And the answer to this is you can use it anywhere except 1D. Okay, so anywhere except 1D. Because the goal of 1D, as I mentioned in the question itself, is to give you a sense of how to prove the structure theorem. Okay, so there's no point assuming one of these things that's stronger than this. Okay, so yeah, so hopefully all of you have understood this point. Okay. Yeah, so any other common question, issues that you've had in the homework? So yes, yeah.
It is the question 1B, linear recurrences t n minus 1 and t n minus plus t n minus 2 plus t n minus 3. So we are having some
complex numbers.
Yeah. Complex.
Okay, yeah. So this one, that handout that I gave you should have something about this. Okay, so yeah, but this one let's come to later. I don't. Yeah. So is this a? How many of you think that this is something I should probably spend a little bit of time about? Okay, it's a significant chunk. So maybe I will. I'll just tell you how. So if you have real recurrences, by real recurrences I mean the recurrence itself has all real coefficients and the initial values are real. So if you have real recurrences where you get complex roots, let me take a simpler example where you have a quadratic. So you have, let's say, plus 2 equals a n plus 1. Can you tell me a quadratic that has complex roots? Yeah, let's start with x squared.
Plus x plus 1.
Okay.
It's strictly constant, so
Yeah, so this is fine, but then the recurrence that shows up from this is a little weird. Okay, but it's fine. So if you have something like this, okay, so if you have a recurrence like this, it's just very weird. So I don't know how.
it's strange algorithm.
Yeah. Anyway, so what you're going to determine is that if you have a recurrence whose solution is of the form an equals some capital A times alpha to the n plus b times beta to the n, c times gamma to the n, c times actually beta conjugate to the n. Okay, where conjugate is a conjugate of this real number. Then first you've got to see if alpha is bigger in magnitude than beta and beta. These two have the same magnitude. So if alpha is bigger in magnitude, then this is the term that dominates. Okay, so it doesn't matter if alpha is real. So if you had a cubic equation, this is what you would get. One root will always be real, and two will be conjugate pairs. And if the real one dominates the conjugate, the complex ones in magnitude, then this guy always dominates. Okay. So this is something you can check. And otherwise, you can try to actually literally solve for B and C. Okay, and express. What you realize is that B and C will be such that all the imaginary terms cancel out. And then you can actually find what this term is asymptotically, because then you can try to write B as some x plus iy. Some cases you can only approximate x and y, that's fine. So you can write this to the n plus the same. Okay, but here it's important to solve for B and C. This is why I give you the base cases. Okay, so using those, yeah.
As we start having those complex numbers, are we going to be penalized for rounding?
No.
Okay.
In fact, yeah, so we'll be very generous with respect to that. The idea is that you know how these recurrences, what these recurrences solve to, and kind of can use some basic facts. Okay, so.
Those complex numbers.
Yeah.
I solved this for that particular problem.
Yeah.
So we do an equation like this.
Yes.
And so one of the roots is real. So, but the multiplier for that, C for that, still turns out to be complex when we apply the initial conditions. But still somehow.
That's very weird. Maybe you should check the calculation.
But when I finally solve put in an I and check the final value for some value of n, for example, the final output is still real. It's still an integer.
Ah, okay.
So though the individual constants still somehow they're complex, but for every value of integer n, it still gives a real number. And in fact, it's an integer.
Okay. Yeah.
I tried for few values, but somehow it's
Okay. I don't know. So try checking your calculation. Usually it's you can get it from the expression. Yeah. Alright, so I wanted to continue the Hamiltonian path problem that we were looking at last time because we left it kind of midway. Okay, so does someone want to recap the algorithm we said? So we were trying to use dynamic programming, right? So this is what we were doing. We said that the key thing in dynamic programming is you should identify the subproblem. Okay? So this is always the first step. Here the full problem is you're given a graph G and your goal is to find a path that visits every vertex exactly once. It visits every vertex precisely once. So, and we started off by saying identify the subproblem. Do you guys remember what the subproblem is? Yeah.
Was that we were going to partition it?
Right, so that was the way of solving the subproblem, right? What is the problem itself? Using two axes, starting. Okay, and what else? Sorry?
Does a path exist between the two?
You mean, does there exist a Hamiltonian path, but is it in the full graph? So what we said last time, if you guys remember, is that it's actually, you also have a subset of the vertices. Okay, so you have some subset of n, and additionally, you have a start in n that belong to this S. And you want to know if there exists a Hamiltonian path in G restricted to S. Okay, so this is usually the notation people don't even write this. So G sub S is the induced, it's called the induced subgraph on S. Okay. So has anyone not heard of this term before? Okay, so it's actually, this looks fancy, but it's very simple. All it means is that it is the vertex set is now S, and the edge set is just all the edges in G, both of whose endpoints lie in S. Okay. So hopefully all of you can see this. So this is the definition of G sub S. So it's a graph on a smaller set of vertices. Yeah, and the same edges as there was in G itself. So that's G sub S, and additionally you have this start and end, and the sub problem is basically does there exist, I'll just call it hamper of G sub S start and finish. Okay, so start. Okay, so when you're trying to solve a problem via dynamic programming, you should try to figure out what the subproblem should be. Right? So, and in this case, this is something we've identified as the subproblem. And in the previous example that we saw of these k types of candy, we said that the subproblem was basically you have a given budget and you are allowed to pick candies of types from I and above. Okay? So that was the subproblem. So there you had, there were only two parameters. So here now you have these three, and this is not really a single parameter, this is actually a subset. So this is actually a pretty big state space. Okay. So just before we get in, so how many candidate subproblems are there? Like if you have a graph on n vertices, how many subproblems do you, suppose I had to like, I try to maintain a table of all possible subproblems. Try building that table, right? Just as we did in the other example. How big would this table be? Is it just 2 to the n?
2 to the power 2 to the power.
Okay, why is that? Somebody said 2 to the 2 to the n.
We'll have to look at the power set for that.
Okay, but how many subsets are there for n? There's only 2 to the n.
2 to the n plus 1.
Okay, so there's 2 to the well, okay, so that's still O of 2 to the n, so that's fine. But we also have the start and the end. So how many more are there?
N squared.
Conservative upper bound is n squared. So n starts and n ends. Maybe not all possible are okay, but this is still a conservative estimate. Okay, so there is roughly this many subproblems. Okay, so the number of subproblems is this. Okay. And one thing to note is that if we are filling out a table, okay, so this will be the size of the table. Okay, so this will in some sense be the memory usage of this algorithm. So I will talk about this point later, but I mean, remember there was a very naive algorithm for this problem, which was check every possible permutation, the n factorial algorithm. So there's an n factorial algorithm that hardly requires any space, right? So you check every permutation, and you just, I mean, you don't have to store the answer for every permutation. You can just check every one, and so it's essentially whatever is needed to store the graph. Okay, so that algorithm actually requires very little space, but it's much more time.
Much more time.
Yeah. So, and here you will actually need similar amount of space and similar amount of time. Okay, but they are both somewhat better. Okay, so these kind of things, so these are called time-space trade-offs that show up in complexity a lot. So, yeah, we'll mention that a bit later. Okay, so now we've identified what the subproblems look like. Right, so now how do we solve a subproblem? Like suppose I tell you, give me a divide and conquer algorithm. So I have G sub S, this is some subgraph. And I have a start, I have a... How would you come up with a divide and conquer algorithm for this? Any suggestions? Yeah.
So one thing we could do would be to identify a vertex in GS which is not S or F, let's say it's V, and call GS S comma V and GS V comma F. Basically,
So you're saying S comma V and then find a path from V to F.
right.
But remember, the answer to this is basically, does there exist a Hamiltonian path between S and F? Right, so if I find a Hamiltonian path between S and V, then I've used every vertex. In particular, I've used F also. Okay, so that's no good, right? So we've got to do something else. So anything simpler?
Partition is that again?
You could partition again, but is there even simpler? Like if there has to be a path going from S to F, right? Could you say something, I mean, could you try to find a shorter path in a slightly different graph? Yeah.
You could remove a node, a vertex.
Which one?
One of them.
Yeah, so actually, no, so that's a natural idea, right? So this is something, somehow I didn't think of it while making the notes for last class, is that if you have S and I want I want a Hamiltonian path that goes to T, and I've stored all the answers for subsets of S. So then a more natural approach would be to say, suppose there were to exist a Hamiltonian path, then I want it to start at S and end at F. So let me try to see what the next vertex on this path could be. Okay? So you could always say, okay, from S, where do I go? And and can you now come up with a divide and conquer algorithm? Yeah.
You could do Hamiltonian path of G and everything except for S, and then something that S has an edge to, so one of its neighbor nodes and F.
Yeah, so you could try all these neighbors, and for each one you could ask, okay, this is G sub S, okay, I remove this little s from this G sub S, I get a different graph. Okay, so this is G sub S minus small s, okay, and this graph just doesn't have S, it has every other node. In particular, it has all these neighbors that are off. Now I say, okay, try to find a path from this guy, from let's say this vertex, and try to find a Hamiltonian path to F. Okay? So, and you could do this for every possible vertex. So, now, why is this algorithm correct? So actually, do you want me to write down the algorithm, or are you guys clear on what the algorithm is? Write down? Okay. So let's call the neighbors of S as V1 through V sub R. Okay. And all I'm saying is call, or rather call, or I will write call, or in brackets I will write lookup. So if I am building a dynamic programming table, then I can just look up in this table. But in a divide and conquer way, I will say call. So call path of G capital minus small s. Okay. And what do I have to do? Call for all I in 1 through r. So what should I call? Yeah. So what should what should I ask, right? So if I wrote ham path of something, there's the start vertex and the final vertex. What should the start vertex be?
One of the neighbors.
So this corresponding vi, right? So for every I should call vi. And the final is still the final. Right? And if one of these returns true, then return true, otherwise return false. So if I'll just return the OR of these. So let me push this up a little bit so that people might not. Okay.
How did you write the subscript of G? S/S.
Oh, okay, sorry. So, in general, if you have a set S and I mean S minus, this is called set minus, S minus some I denotes, if I was in the set, then I remove that, otherwise it's S itself. This is a standard set difference notation. So I've used that with I being this little s. So yeah, it's a good question. So any other? Yeah.
Is the base case when G sub S minus S is just 2 nodes?
Yes. So the base case is just 2 nodes, or you could even say 1 node, in which case you can always trivially output yes. So yeah, any other? And what he said is important because whenever you write a recursive algorithm, you've got to make sure that there's some monotonicity, right? That you don't recursively call the same thing again. And in this case, you never do it because the size of this set keeps reducing by 1. Okay, so you never have cycles. Okay, so more questions on that? Yeah.
Do we need to repeat this for every node has finish too?
You're saying in principle, I don't care about the finish. Yeah, probably not. Yeah, you could just say this for. Yeah, you can use this kind of an algorithm to solve even the problem where you don't care about the finish node. Yeah.
Because here are we fixing the finish node?
I mean, I am fixing the finish node, but maybe you don't need to, right? So if your goal is just to find a Hamiltonian path in the full graph, I mean, you don't necessarily need a fixed finish node. I am trying to solve a slightly harder problem of is there a path between, starting with S and finishing in F. So yeah, so maybe that still works, but yeah.
So if we don't have a finish node, how will we argue? I mean, if we are actually finding.
Right, so let's argue for this version, then we can try to argue for that. Okay. So here I kept everything simple in the sense there is a start node, there is a specified finish node that I know. So yeah, so in this case, suppose I have to show that this algorithm is correct, right? So that this divide conquer set is correct. How would you argue?
case is correct, or true?
Yeah, so true. The base case is true. And the base case is 1/2 node. Okay, and what about the inductive step? Now you'll say, assume for all sets of what? So how would you now run this induction? Yeah.
So if we have a path from S to intermediate node Vk, we can always find a path from Vk to Vk plus 1.
Wait, so you're not talking about my VKs. My VKs are just neighbors of S. There's no.
Any vertex between S and V. If we have a path between S and V, we can always find a path between S and V plus 1.
Okay, why?
Because we will explore all the neighbors of V.
Yeah. So but Vk plus 1 is not a neighbor. So are you assuming there exists a path which is S, V1, V2, something
Yes.
else? Okay. So, right. Okay, fine. Maybe something like that could work. But firstly, what is your, when you're proving something by induction, right? You've got to say, I will assume this for all objects of certain property, and I will prove this for all objects of size k plus 1 or something like this. So how would you say, what is the statement I've got to write?
If there is a Hamiltonian path for a graph of, if this algorithm says there is a Hamiltonian path for a graph of size n,
Yes, that's the final claim that you want to prove.
we
Right?
assume that it does that.
So that's the, okay, so what I mean by correctness is that if a subgraph, if lambda G sub S S F returns true, there is a real, there is a Hamiltonian path. So S and vice versa. And vice versa is just, if there is a Hamiltonian path, then the algorithm also returns true. Okay. So this is the statement that we want to prove here. And what he said is that this statement is trivially true for the base case. Okay. Now how would you set up the induction?
If there are only two vertices, that is the base case, and there is a path, this path has to be Hamiltonian path.
Okay.
And if there is another one, so the last recursion call returns true, and for the previous one, if it returns the true, it will check whether this one returns true or not. If this returns true, then Vk minus 1, that one is also part of Hamiltonian path. So I will keep on checking like that.
So you're essentially saying that somehow the size of the S is the key thing that matters. Right? So you prove it for 2, you prove it for 3, sets S of size 3, sets S of size 4, and so on. So when you are saying things like this, you basically say we use induction on the size of the set S. And ultimately we will use it for the full graph which has size n. Okay, so that's the way you formally say what you were just saying. Okay, so this is, the proof is by induction on size of the set S. Okay, and the base case is trivial. These are size of S equals 1 or 2. And now the inductive step is clear, right? So you say that assume true for all size of S less than k and prove it equals. If you want to be nice, then right. Okay, so this is what we mean by induction on the side effect. Because first prove the base case and then say that if it's true for all numbers up to a certain point, it's true for the next number. So this is what we would like to show. Yeah.
So the initial statement which we are trying to prove, right, if ham path returns true, there is a path. That is what we are trying. Should we
Yeah.
also prove the reverse of that?
Yeah, once say for all s, if ham path returns true, there exists this, and vice versa. So you should also say. Okay. So this is what. So yeah, good question. So any other? Okay, so now let's show this. So the base case is easy, so all we have to prove is this inductive case. Right, so let's try to prove it. Alright, so how would you prove it now? So that is the recurrence. And intuitively, many of you seem to agree that this algorithm works. Right, so how would you now formally say that this, yeah?
If it gives a Hamiltonian path till k minus 1 node, then since in the algorithm we are checking all the neighbors, so it will only give a Hamiltonian path in k if there is an edge between k minus 1 and k, because since we are checking all the neighbors.
Yes, but right, I agree that that's roughly the idea, right? But what you're saying is, I mean, can you pinpoint? Can you say that again?
Since we have already assumed that if there is a Hamiltonian path from a start node till k minus 1, it gives true. So if there is a Hamiltonian path from S to k, it will give true only if there is edge from k minus 1 to k.
Okay, so what you're saying is, like if we look back at this statement that you want to prove, you're saying that you're trying to prove the vice versa part, right? You're saying if there exists a Hamiltonian path in G sub S, so what you're saying is essentially that let's consider any S of size K. Okay, let us consider any S of size K. Okay. And we are assuming that our hypothesis is true for all S of size strictly less than. And we are trying to prove it for this S. So, and what you're saying is, we've got to show two directions, right? One is, if Hamiltonian path returns true, there exists a Hamiltonian path, and vice versa. So you're first stating the vice versa part. Okay, you're saying if graph has, this is the vice versa part. Okay, if G sub S has a Hamiltonian path from S to F, the algorithm returns true. Right? So this subroutine and the reason is exactly what she was saying, that suppose there is a Hamiltonian path, then this one is supposed to start with S and is supposed to go to F. Okay? Which means, and it should cover everybody in S in between. Maybe the path looks more messy. It looks like this, and it goes to F. Okay, it covers all the vertices and goes to F. And so it must have, now let's look at the second step in this path. And that is a neighbor of S, so that will be enumerated among one of the VIs. And so for that reason, if you removed S from here, try to find a path here, I mean, because of the inductive hypothesis, you should have got the right answer. So that's how you would formally say. Okay, so you would just say that if GS has a path from this, subroutine returns true, and the reason is that if we consider the true path, if we consider the true Hamiltonian path, there should be some Vi, which is the second element in this path. And for that I, this expression would have returned true. Okay, that's why the OR is true. Okay, so that's the formula. Okay, so let me not write this. Okay, so now, what about the first part? That if the algorithm returns true, then there exists a Hamiltonian. This also, in problems like this, these things are all very similar, so you should be able to.
Yeah, so if there is a Hamiltonian path for k minus 1 vertices, and I need to plug in the kth vertices, and the algorithm returns true, so that means that kth vertices is a neighbor of k minus 1, so that is there is a path between k and k minus 1, and as k minus 1 covers all the vertices, so I don't need to talk about it, so k is in the Hamiltonian path of k vertices.
Yeah, so what roughly speaking is saying is that if you, let's say the algorithm returned true, the final algorithm returned true. The only way, because it's taking an OR of a bunch of things, so that means there existed a Vi for which it was true, for which the Ham path was true, means that I can break this graph into S and some Vi and this. And a graph which does not contain S, right? So with S minus small s. And now I can use the inductive hypothesis to say that if Vi, f is true, there exists a Hamiltonian path in S minus S. Okay. And now consider this new Hamiltonian path that includes S. This is Hamiltonian because it covers every vertex precisely once. And because of this is a Hamiltonian path for all of S. Okay? So that's this is actually the easier direction in this case. So so that's the I just wanted to formally do this because many of you keep asking, okay, how do you write proofs formally and stuff. So that's why I want to. In some of these cases, I would like to just spell out the details. So, good. Okay, so this is. So, any questions on that proof? Yeah. In which part? In that part? Right. So, what we are saying is, let's suppose the algorithm returned true, right? The algorithm returned true. So what does the algorithm actually returns? It returns an OR of all these things. Okay. If an OR of a bunch of quantities is true, means that at least one of them is true. Okay. So I'm letting that one guy be Vi. Okay. So that's how I pick the weight. And then we know that if I removed little s from this capital S, then there is a Hamiltonian path from Vi to F. To that path I am just appending S because S is a neighbor of U by definition.
So with this algorithm, if we don't find a Hamiltonian path, so then do we take a different combination of S and F?
Yes, I haven't told you how to, so basically you're saying this way I have actually defined a start and a finish while the original problem did not have a start and a finish.
Because there might be a Hamiltonian path, but it not be between two.
Right. Yeah, so you have to search for all possible start and finish. There's only n squared of them, right? So we are dealing with algorithms of runtime 2 to the n. So n squared is just the change, copy change. And so that's the rationale. Okay, so this is this is what I wanted to just finish up, and I wanted to say explicitly what I had said some time ago, that this algorithm, if you now try to remember all these values, right? So we know that there are only 2 to the n times n squared subproblems. So you can say that we keep an array, an array or a table, right? So keep a table of size 2 to the n times n squared. And how do we fill this table? So this is the other thing you've got to think about, and the answer is in the proof. So what order do we fill the table?
Starting with the base case when there are only 2 nodes.
Yeah, so we fill the table using, increasing order of the size of S. So the table has size of S, the starting vertex and the finish vertex. The set S, starting vertex and finishing vertex. And now we say, okay, I fill this table based on increasing order of size of S. Initially I do it for S of size 2, S of size 1 you can trivially always have yes, and this is how you can do it. Right, so this is how we fill the table, and how long does it take to fill one entry given that algorithm? How many lookups are you doing to fill one entry?
Neighbors and neighbors, so
Yes, the number of neighbors of that S, which is at most n. Right, so every entry can be computed less than n. Okay, and this gives a total running time of 2 to the n times n. Okay, because there's 2 to the n times n squared entries, each one takes n time. And this is time. And space is 2 to the n times. So actually, using an idea that somebody was saying, maybe you don't need, if you don't literally care about the start and finish, you might be just able to ignore the finish. You can just say, is there a Hamiltonian path just starting at this S? I don't care where you end up. Okay, and then, so I would guess that the same kind of analysis would work. Okay, so that's the exercise for you guys, if you want to think about it. So, and that would give slightly better running times. You have 2 to the n times n squared and 2 to the n times n. And but it's not much because we already have a 2 to the n that dominates the running time. So that's why you don't have to guess. So that's the thing I wanted to say. So this is an algorithm where both the running time and the space are roughly 2 to the n. Yeah.
If 2 to the n is the dominant, why we need to times it, times the n to 3?
Oh, so it's dominant in the sense that, for any n that's large enough, 2 to the n is significantly larger than n to the 3, but the actual time complexity is still there. It's 2 to the n times n cubed, right? That's what the algorithm gave us. This is a matter of this is an intuitive way of understanding things, right? When you say a running time of n log n, okay, sure there is the log n, but in some sense it's it's very close to n, right? N is often the dominating factor. So yeah.
So when we divide, we're only dividing and then the rest, so that doesn't really give you that much of an advantage. Are there other algorithms that have like similar running time that aren't divide and conquer?
Yeah, so that's what I wanted to mention, that this is actually a big open question. Okay, so if you look at time-space trade-offs, right? So if you time-space usages. Okay. So the trivial algorithm that basically checks every permutation of the vertices. Okay. So this has time n factorial, which is like n to the n, and space just linear. Okay, so this is O of n squared at most. Okay, so space is just polynomial. While this messy algorithm, this dynamic programming algorithm, here, I mean, this is like 2 to the n times n squared, or yeah, n cubed. This 2 to the n. So you could ask, is there an algorithm where here you have poly n, and here you have something like 2 to the n times poly n? This is actually one of the big open questions. People don't know if you can get algorithms of this kind. Okay, so, so people think that this kind of time-space trade-off is necessary for this traveling salesman type problem. But we don't know. This would be a very interesting result if you could actually get an algorithm of this kind. Something that you guys mentioned. So, okay. So anyway, so this is what I want. This is how I wanted to conclude dynamic programming. So basically, you've got to think the way we thought. Okay. So you want to come up with a divide and conquer algorithm. And you say, what does a sub-instance look like? Then you try to say there aren't too many different sub-instances. And in some sense, I memorize the answers to all of them. And this is how you analyze the running time. You try to say, okay, I have this table. How much storage do I use? How much time do I take to fill one entry? This is how you typically answer. Yeah, this is how you go about doing dynamic programming. So next.
Is it always that we reduce it by 1? Because you're saying
no, not always.
But we're not really dividing it into n.
Yes, so that's, yeah, so I mean, that's why the last class, I thought that this is a good example for doing partitioning and stuff, but then I realized that, oh, you don't really need to partition into 2, you can just divide it into 1 and n minus 1. So, yeah, so that's why, very great example, but there are examples where you can actually, to do like clever partitions.
Which use dynamic programming?
Yeah.
We do not need to split and to find a connection between the two splitted parts. We just take the entire graph and we run the other.